Okay, so I had gotten an email asking for me to review a few things from Chapter 6 and Chapter 7. Oh, I need my calculator. So I'm going to try to get it all into one video, but if it takes two or just a really long one video, we'll go from there. But first off, harmonic motion. So we know as far as harmonic motion goes, we have the standard equation. For simple harmonic motion, there's damped harmonic motion, but we're only worrying about simple. D equals A sine omega t, or we can have A cosine omega t. And as I said before, just keep in mind, this A, it's the amplitude of my spring because it's the amplitude of the wave, just like it was before. I know omega is just the thing that's going to stretch or compress it, which really just means that, well, it's going to change the period. And we have that trick. We just do 2 pi divided by omega to get the period. The one difference maybe is here we can have a frequency. When we talk about a spring, the frequency is just omega over 2 pi. The reciprocal of the period. And one thing I would point out, because based on labs and homework people get confused here, just find your period, just like you normally do. Don't even think about the frequency. Find your period like you normally do, and then don't try to plug into this equation, because based on past experience, when students do that, they get it wrong. Find your period, and then do 1 over the period, and be done with it. That's the definition. This is the more algebraic way of writing it. Find the period like we know how to do, and then do 1 over that, and you're done. And you can then simplify the resulting fraction or throw it into your calculator. So ultimately we understand the way this works is we want to be able to take a real world problem and then create an equation from it and use it to then answer other questions. Also understand this is the standard equation, but occasionally from a real world perspective, we shifted our springs around, sometimes from the ceiling, sometimes we pulled them left or right, things like that, which meant we might have to manipulate our equation slightly. But just to do an example, suppose I have this, let's see. I attach a spring to the ceiling, which is 8 feet high. I pull it down 6 feet, which is its total length. And release it. It takes, let's see, we'll say 2 seconds to complete 1 cycle. Find an equation that models this. And in theory from there, we could then say, kind of like on your lab, where would the spring be after 3 seconds or 7 seconds or whatever. Once you have your equation, you can just plug that number in and hit enter on your calculator. So I'm not really worried about this here. But I want to create an equation. First thing we can do, as we've said repeatedly for trig, draw a picture. So if I draw a picture, there's the floor, there's the ceiling. I attach a spring to the ceiling, which is 8 feet high. So that's 8. I pull it down 6 feet. So that's a distance 6. I release it. And now when I released it, what happens? Since I pulled it down, it's going to go up to the top, which we'll assume is right back at the top of the ceiling, since that's where it started. And then it'll start going back down again until it reaches its lowest point. And then it'll keep on going. We understand in the real world it'll ultimately stop because it's damped harmonic motion, but here we assume it doesn't. So if I now look at the picture, it does that. There are different ways to model this. You can actually model it with either of these. One of them will be messier than the other. The way we generally set it is, if we think about our trig, we have 3 waves. We have a sine wave, Well, actually, we could have a sine wave, which starts at equilibrium, goes up and down. You could also flip the sine wave, which starts at equilibrium and goes down and up. Then we have a cosine wave, which starts at maximum, goes to minimum, and then back up. And then we could do the same thing. We could flip the cosine, started at minimum, and go to maximum, and then back down. And I pick the equation that works best with that. In this case, I'm starting at my lowest point, going up to the highest point, back to the lowest point. That's this one right here. That's a cosine flipped, which tells me I should use the equation y equals negative a cosine omega t. And I understand I might have to manipulate this a little bit more at the end because it's a real world problem. And again, from a homework perspective, I guess, if we said I started the spring right in the middle and released it and it went down and up and all of that, if I started with a displacement of 0, then we would go with the sine wave because I'm starting at 0 at displacement of 0, however you want to say it. First off, I need an A. I know that's amplitude and I know the trick. Amplitude is the total displacement divided by 2. Here, the string stretches 6 feet total, which means total displacement is 6 feet. Amplitude has to be half of that, 3 feet. So A has to be 3. Omega is, well, the thing I use up here to get my period. I'm told it takes 2 seconds to complete 1 cycle, which means my period is 2. So now we just kind of backwards engineer this. 2 pi over omega has to equal my period, which is 2. Now just solve for omega. Multiply the omega, we get 2 pi equals 2 omega. Divide the 2 on both sides, we get pi equals omega. So now, omega is equal to pi. And now, like I said, I didn't ask it here, but if I was told to find the frequency, don't use that, it tends to confuse people. By definition, the frequency is 1 over the period. Period is 2, the frequency is 1/2, and you're done. If we remember the terminology, frequency is how much you get done in 1 second or 1 unit of time. If it takes 2 seconds to complete it, I get done half of it in 1 unit of time, 1 second. So it makes sense. Okay, so now this is my wave. The problem is we said the assumption here is that all of these waves start like at 0, 0 at the origin, but in the real world we shift things around and make it more realistic. In this case, I don't have to shift it horizontally, don't worry about any of that. But I assume that this is height 0, which means my wave is actually shifted because it's not starting on the origin there or starting at minimum or anything like that. But the trick to this, think about a regular cosine wave. Normally, for this wave, I would start at -3, my minimum. Then I would go up to +3, which is my maximum, and then back down. So my wave is going to look like that. Don't worry about the actual x values because of the period and all that. I just want a rough sketch. What does this wave do? The ceiling is 8 feet. The string gets pulled down 6. The spring gets pulled down 6 feet, which means it's 2 feet off the floor. Which means it's starting at a height 2. Then it's going to go up and down. Its maximum height is the top of the ceiling, which is 8. How are those waves different? This starts at -3. This starts at 2. It's clearly up 5. To check that, this ends at 3. This ends at 8. It's up 5. So now, on the end of my wave, just add a +5. Now I have this wave right here, which is the original one I modeled, but now I shifted it up just to make it match up with the picture here. The other thing I would say on this, keep in mind, a lot of times when we do the spring, I prefer to pull them up and down simply because in the real world, that's how I view springs, going this way. But from a physics perspective, you can also pull springs sideways. If I pull it and start over here on the positive side, that's like starting on the positive side here, cosine wave. If I pull it over here, I'm starting on the negative side. That's like pulling it down, starting on the negative side. That's a negative cosine. Up and right are positive, down and left are negative. So just kind of keep that straight in your head as you're working through these. This video is already over 10 minutes long, so I'm going to stop it and make another video doing the other stuff, just so you don't have to sit through a really long video if you're only looking at one or two things.